Hello there and welcome back to the Sleep Science, where tonight you're not slipping into bed, you're slipping into a photon. Not beside it, not chasing after it. No, tonight you are the photon. You have no mass, no need for breakfast, and absolutely no chill. You're moving at exactly 299,792,458 meters per second. That's the speed of light if you didn't catch the digits. Right now, you're zipping from the surface of the sun to Earth in just over 8 minutes, and somehow you still manage to be late for every meeting. It's not your fault, though. You exist in a very weird place where time is, well, kind of broken. Imagine blinking and seeing the entire journey flash past you in a single, compressed instant. There's no before, no after. For a photon, the concept of time passing doesn't really apply. It's like experiencing an entire road trip in one eternal frozen moment. You are movement incarnate, but trapped in timeless stillness. Yeah, it's going to get a little existential. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, post your location and your local time. I love seeing where and when you're tuning in from. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You tumble through the vacuum like a needle through silk, fast, frictionless, and shockingly unaware of anything around you. As a photon, you don't get to stop. You can't. There's no rest frame for you. Even if the universe begged, you couldn't hit pause. You're pure energy, completely massless, and by the laws of physics, you are forever condemned, or blessed, to move at the exact speed of light. But here's the catch. You don't feel like you're moving. Inside the frame of a photon, there's no time. From your perspective, the moment you're created is the same as the moment you're absorbed. There's no in-between, no travel time. It's as if space itself collapses down to a single point. That 8 minutes to Earth, from the outside, sure, but from your point of view, instantaneous. A one-frame movie. Let that bake your noodle for a second. And here, where things start to stretch out both metaphorically and literally. Time, as it turns out, is squishy. When you start approaching the speed of light, time behaves less like a clock and more like a wet spaghetti noodle left in the sun. The faster you go, the slower time ticks. At light speed, time just stops ticking entirely. This is not just some poetic interpretation. It's been clocked, measured, verified. High-speed particles, muons for example, live longer when they're zipping through the atmosphere at relativistic speeds. We're talking subatomic geriatric miracles. It's all due to time dilation, a now famous prediction of Einstein's special theory of relativity, published back in 1905. Now we know what you're thinking. Cool, so if I were a photon, I could technically cheat time. Yes, but also no. Because remember, you're not just moving fast, you've become something that must move fast. Anything with zero mass has no choice but to travel at the speed of light. The universe doesn't give photons options. There's no casual walking pace mode. There's no Monday morning crawl. Just maximum velocity all the time. Historically, light was a mystery wrapped in an enigma wrapped in a scarf that smelled vaguely like candle smoke. Ancient Greek philosophers argued about whether light was a particle or a wave, or even a substance that emanated from your eyes like little vision tentacles. Yes, that was a real theory. Empedocles, we're looking at you. Then came Newton, who suggested light was made of particles. A few centuries later, along came Huygens with his wave model. Back and forth it went until the 20th century said, why not both? Modern physics says light behaves as both a particle and a wave, depending on how rudely you observe it. Quantum mechanics is basically the physics version of Schrödinger's cat and an IRS audit at the same time. But even with all that strange duality, one thing about light remains beautifully rigid: its speed. In a vacuum, nothing goes faster. You can't upgrade your photon to turbo addition. It just is. And that fixed velocity has massive implications, not just for how we see the world, but for how the universe functions. Here's the cheeky reality check. You probably won't survive this. Not because you're in danger, but because you can't exist as a photon. You, dear listener, are gloriously, frustratingly full of mass. You're matter, and matter plays by different rules. The moment you have mass, the door to light speed slams shut with a thunderous note. The closer you try to get, the more energy it takes. Double your speed, that's fine. Triple it, sure. But try to get within a hair of light speed, and suddenly you need infinite energy. Infinite. That's like trying to pay off student loans with a sandwich. Scientists have chased this limit with everything from particle accelerators to theoretical equations scribbled on chalkboards at 3 a.m. And so far, the cosmos remains annoyingly consistent. Light speed is the ceiling. There is no breaking it, no loopholes, no cheat codes. If you have mass, you stay under the line. End of story. Well, almost. Historians still argue whether Galileo, that telescope-wielding rebel, had any inkling of how time and speed were secretly entwined. Some say he merely planted the seeds. Others insist he must have suspected the universe had a deeper rhythm, hidden behind the motions of stars and pendulums. Regardless, it was Einstein who pulled back the curtain and revealed the gears. The speed of light wasn't just a number, it was the speed limit of causality itself. So here you are, drifting across the cosmos not as a person, not even as matter, but as a flicker of electromagnetic energy, timeless and tireless. You are a reminder that in this vast, chaotic universe, some things are absolute, and that's oddly comforting. Even when everything else is falling apart, photons don't miss appointments. You keep soaring, still inside that relentless beam of light, weightless, ageless, and frankly, a little smug. After all, you've hit the universe's top speed without even trying. But while you're busy basking in your massless glory, something peculiar is happening behind the scenes. From the perspective of literally everything else, not you, time is moving along just fine. Clocks are ticking, suns are setting, and people are overcooking pasta. But not for you. You're stuck in the ultimate now. And here, where the questions begin to bubble up, especially if you're the curious type. Why is it that you, as a photon, can experience no time at all? What's so special about this 299,792,458 meters per second number that it makes time slam to a halt? Couldn't the universe have picked a more rounded number? Maybe 300 million, just to be tidy. Nope, the cosmos, it turns out, doesn't care about your need for numerical elegance. That number is baked into the very geometry of spacetime. And it's not just really fast. It's not maximum effort fast. This is the structure of reality fast. Time dilation, that slippery concept we teased earlier, isn't just a curiosity. It's a direct consequence of the rules built into the way the universe handles motion. The faster you move through space, the slower you move through time. Imagine spacetime as a budget. You get a fixed amount of motion per second. If you spend more of it moving through space, you have less to spend moving through time. Think of a loaf of bread. Thick slices mean fewer slices in total. If you're slicing time thick because you're barely moving, then you experience more of it. But if you're slicing it thin because you're flying through space like a caffeinated photon, there's hardly any bread left to taste. By the time you hit the speed of light, you're all motion and no time. Your bread is a cracker. This isn't just theoretical, it's observed. GPS satellites circling Earth at high speeds have to account for time dilation, or your phone would tell you you're in the wrong coffee shop. Muons created by cosmic rays reach Earth's surface in greater numbers than expected because, in their speedy little frames, time crawls and decay slows. These aren't sci-fi oddities. They're everyday consequences of living in a relativistic universe. Still, your mind itches. Why this speed? Why the speed of light? What if something tried to go faster? And here, we hit the metaphysical guardrails. As you approach light speed with mass, a spacecraft, say, or an unfortunate squirrel in a hypothetical cannon, something nasty happens. Your energy requirements shoot through the roof. Not linearly, not even exponentially. We're talking about an asymptotic wall. You get closer and closer to the speed of light and your mass appears to increase. Not physically, don't worry, you won't suddenly need new pants, but relativistically. From an outside observer's point of view, you're heavier, denser, more stubborn. To push a speck of dust to light speed would require infinite energy. Not a lot of energy. Not drain 3 stars and hope for the best energy. Infinite. The kind of number that breaks calculators and friendships. And that's not something the universe casually allows. Physics, for all its beauty, is surprisingly frugal. But there's an even more unsettling consequence to consider. As you inch toward light speed, time slows not just for you, but in how others perceive your timeline. You, aboard your hypothetical ship, might experience minutes while the outside world watches years tick by. Push it further and those minutes could encompass entire centuries back home. At light speed, game over. From everyone else's perspective, you never age. From yours, there's no you to age at all. Now imagine trying to go faster than light. What would that even mean? If light speed halts time, would faster than light travel reverse it? Would you arrive before you left? Would you undo breakfast? That's where things get dangerously philosophical and deeply problematic. See, special relativity doesn't just say you can't go faster than light. It shows what happens if you could, and it's not good. You'd break causality. Imagine this. You send a message faster than light. To someone else, it arrives before you even finish typing. With the right configurations, that person could respond before you sent the original message, which means you receive a reply before you had the idea to write it. Congratulations, you've invented a time loop, and probably an existential crisis. Historians still argue whether Einstein himself fully grasped the implications of faster-than-light travel when he first published special relativity. Some of his later writings suggest he suspected the rabbit hole went deeper than even he could see. But by anchoring the speed of light as an absolute maximum, he essentially preserved the universe's sense of cause and effect. No matter how wild the equations get, the story always happens in the correct order. You might be tempted to think of light speed as a kind of cosmic speed bump, but it's more than that. It's a wall made of logic and consistency. Allowing anything to move faster wouldn't just mean rewriting equations. It would mean tearing apart the very logic that holds reality together. Of course, fringe theories abound. Some speculate about tachyons, hypothetical particles that can only move faster than light and never slower. These particles would always experience imaginary mass. Yes, imaginary as in involving square roots of negative numbers, and theoretically travel backward in time. That's the physics equivalent of a roommate who only moves in reverse and borrows money before asking. We'll chat more about them later. But for now, bask in the paradox. The universe sets a speed limit not because it enjoys rules, but because those rules are the universe. The fabric of spacetime, the stretching of time, the inflation of mass, all of it emerges from this simple, beautiful constraint. Nothing goes faster than light. And you, floating timelessly as a photon, are the only one who doesn't feel it. For everyone else, the speed of light is the line between possible and absurd. For you, it's just Tuesday. Your glide through spacetime continues, effortless, undisturbed, but also undeniably strange. If you had thoughts as a photon, they'd probably sound like static in a wind tunnel, or maybe an overly dramatic audiobook narrated at 10,000 times speed. But lucky for you, we're still tagging along with our oversized human brains, trying to make sense of the absolute weirdness you're wrapped in. At this point, the scenery starts to warp. Not visually. You can't exactly enjoy a sunset when you're the beam causing it, but conceptually. You're now entering Einstein's old stomping grounds, and he's about to drop a truth bomb so elegant and so deeply uncomfortable that it changes everything. Space and time are not separate things. They're a single entity, space-time. Sounds simple enough, right? Just squish two words together like peanut butter and jelly and call it a new thing. But what that really means is that moving through space necessarily alters your movement through time. It's like a budget you don't know you have until it's suddenly maxed out. You only get so much motion credit, and light speed spends it all on the spatial side. Time, canceled. You're broke. This is the core of special relativity, published by Einstein in 1905, back when people still got their physics news from telegrams and awkward monocle conversations. The idea was radical. The laws of physics are the same for all non-accelerating observers, and the speed of light is constant no matter how fast you're moving. It doesn't care if you're walking, flying, or attached to a shopping cart rolling downhill with groceries. Light speed is always the same, period. Now, what makes this so annoying and so brilliant is what it does to our intuitive understanding of the universe. Before Einstein, speed was simple. You add things. You run at 5 mph on a train moving 60 mph, and you're going 65 mph relative to the ground. Easy. Newton would nod. But light doesn't play by those rules. If you shine a flashlight while on that same train, the beam doesn't go 60 plus C, it just goes C even for someone watching from the station. That light is still moving at the speed of light, not a hair faster. That's like baking a cake and finding it always takes exactly 30 minutes to cook, whether you're at sea level or falling out of a plane. How does the universe make this work? Simple. It bends space and time to compensate. Time slows down, distances contract, and reality twists itself into a pretzel to ensure that light always travels at that one unflinching speed. There's a reason why Einstein's insight was so earth-shattering. It didn't just revise Newton's equations, it rewrote the very stage that all of physics performs on. And tucked inside that rewrite is the reason you can't go faster than light, because doing so would break the geometry of spacetime itself. As you, our gallivanting photon, continue zipping along, you exist in a world where these limitations no longer apply to you. You're already at the limit. But for anything else, the closer it tries to push against that wall, the more spacetime pushes back. Mass increases, time distorts, and energy demands spike. Try to go faster, and the math flips a table. Here, where things get poetic. Mass and energy are not just close friends, they're the same thing in different outfits. That's the magic behind Einstein's most famous equation, E equals mc2, a deceptively simple formula hiding a cosmic revelation. Energy and mass are interchangeable. They are the same currency, just cashed out in different ways. The C2 part, that's the speed of light squared, a huge number, which means even a little bit of mass contains an enormous amount of potential energy. Drop that idea into your morning tea and stir gently. But it gets weirder. Because of that relationship, as you pump more energy into a massive object, trying to accelerate it toward light speed, you're also increasing its relativistic mass. It's like trying to push a swing that gains weight every time you give it a shove. Eventually, your swing is a small mountain, and you've run out of juice. This is why no spacecraft, no particle, no heroic astronaut with a rocket strapped to their back will ever hit that elusive velocity. Not because the engines aren't strong enough, not because the fuel's too expensive, though fair, But because physics flat out refuses, the closer you get, the more the universe drags its feet until the amount of energy needed becomes functionally infinite. It's the cosmic equivalent of being ghosted by reality. Historians still debate whether Einstein truly understood the cultural explosion his theory would cause. Some say he knew he was rewriting the rules of everything. Others argue he just wanted a better way to explain inconsistencies in Maxwell's equations. Regardless, what emerged was a model that's been tested again and again, with atomic clocks on mountain tops, with satellites in orbit, and with high-speed particles in accelerators. Every time the results agree. Light speed isn't just fast, it's fundamental. Now here's a fringe tidbit you didn't ask for but absolutely deserve. There's a theory that the speed of light hasn't always been the same. Some cosmologists speculate that in the early universe, right after the Big Bang, light may have traveled faster. A different speed limit in the baby universe. It's speculative, controversial, and extremely difficult to test. But it's a reminder that even the most universal constants might have histories we don't fully understand. Still, for now, the speed limit holds. No cheating, no bypasses, no express lanes for billionaires. So you continue basking in your photonic perfection. You are the blueprint of motion. You are the reason shadows exist, the reason plants grow, the reason we see anything at all. You don't need to age. You don't even need to arrive. You simply go. And for everything else in the universe, going is an exercise in compromise. Light speed isn't just a goal, it's a boundary, not set by governments or policies, but by the fabric of existence itself. It's not there to frustrate us. It's there to keep the machinery of reality from spiraling into chaos. So take comfort. The laws may be strict, but they're reliable. And somewhere out there, probably on a chalkboard at 2 a.m., another physicist is falling in love with them all over again. You're still humming along as a photon, weightless, wordless, without even a vague sense of what day it is, when the question suddenly tightens around the whole experience like a zipper. What happens if something could go faster than you? It's not just a what if to toss around at 2 a.m. while staring at the ceiling and wondering if you left the stove on. This question messes with the very wiring of the universe. Because when you poke at the idea of breaking the light speed limit, you're not just asking to go really, really fast, you're asking to mess with causality. That's right, the golden thread that holds reality together, cause then effect. First you sneeze, then someone says, "Bless you," in that order, always. But let's say you invent a magical ship, shiny, chrome, powered by caffeine and bad decisions, that can move faster than light. It takes off from Earth at warp speed and heads for a distant planet. You've programmed it carefully. But to an outside observer watching from a third location, something fishy happens. They might see the ship arrive before it leaves. Not just from a scheduling point of view. This isn't like showing up for a party early and awkwardly helping with appetizers. This is full-blown time inversion. The effect comes before the cause. From your point of view, you're just cruising along. From another observer's perspective, you're traveling backward in time. And if that ship could send signals, say, a friendly postcard from the future, those messages could also travel in reverse, arriving before they were sent. With the right arrangement, you could build a loop, send a message to yourself that prevents you from sending the message. The result, reality glitches out. You've created a causal paradox. And probably some kind of interdimensional paperwork. This isn't just speculative anxiety. Physicists have crunched the numbers, and yes, going faster than light opens the door to close time-like curves, scenarios where an object loops back into its own past. It's like tying your shoelaces only to realize your entire leg is inside the knot. Logical paradoxes bloom instantly. Can you prevent your own birth by sending a faster-than-light telegram? What does before? even mean when clocks start disagreeing with each other about the order of events. Einstein knew this, and his theory elegantly protects against it by locking down that cosmic speed limit. If nothing can outrun light, then causality is preserved. You can never reach a point in spacetime before an event that affected it. The rules hold. The story unfolds in the right sequence. And to understand why, you have to shift how you think about speed. See, most people picture speed as something linear. Faster means sooner. You cross a distance in less time. Simple. But in Einstein's universe, faster through space can actually mean slower through time. You're not just moving through coordinates, you're carving a path through spacetime, and every path has consequences. Here, where it gets spicy. In the fabric of spacetime, every event sits inside something called a light cone. It's not an actual cone with sprinkles, though that would be nicer. It's a diagram showing what's possible causally. The top of the cone contains all the events that can be affected by a given event, and the bottom holds all the ones that could have caused it. Anything outside the cone is causally disconnected. There's no influence, no interaction, no hope of syncing up. If you move faster than light, you jump outside that cone. You're no longer causally related to the events around you. It's like ghosting reality while still expecting it to answer your texts. Doesn't work. This structure is baked into the equations. The light cone isn't just a handy metaphor, it's how spacetime enforces the rulebook. Every photon traces the edge of the cone. Every possible signal, every interaction, every consequence is confined inside. You want to stay connected. Stay inside the cone. The second you step out, you're not just breaking speed, you're breaking logic. Now, there are fringe interpretations, of course. Some physicists toy with retrocausality, the idea that effects can influence causes under specific quantum circumstances. In a few bizarre interpretations of quantum mechanics, such as the two-state vector formalism, time may be more flexible than we think. But these theories are delicate, hotly debated, and definitely not invitations to build a faster-than-light Uber. Historians still argue whether earlier thinkers, like Henry Poincaré or even James Clerk Maxwell, ever suspected this deep entanglement between speed and causality. Some letters suggest they were sniffing around the idea, but Einstein pulled the whole thing together with his obsession for symmetry and his uncanny ability to imagine riding on beams of light like a Victorian cowboy. But let's not get too lost in abstract diagrams and paradoxes. Let's get back to your ride. You're still a photon, remember, still racing across the vacuum like a cosmic express train with no brakes and no concept of arrival. And as you continue to zip along, oblivious to time and unable to stop, you act as a boundary, a universal edge. Everything behind you obeys the rulebook you define. Everything tries and fails to catch up. This rule, this limit, this barrier, it's not arbitrary. It's the result of how space and time themselves are woven. That fabric resists being torn. Let one thread move faster than light and the whole tapestry starts to unravel. Cause and effect become confused. Histories collapse. You don't just risk seeing your grandmother before your parents meet. You risk watching lunch arrive before it's cooked. And no one wants time-traveling salmon. So the universe says no, firmly, absolutely, and quietly. It wraps causality in a cocoon of light speed limits and says, here and no further. You may dream, you may speculate, but you will obey. Not because of some external law, but because of internal necessity. Because without that limit, nothing, literally nothing, makes sense anymore. And that's the funny part. We often imagine physics as a cage, as a cold set of restrictions. But in reality, it's the opposite. It's the net that holds up everything else. The light speed limit isn't a burden. It's a blessing, because it lets things happen in order. It lets stories unfold without glitching. It lets cause and effect take turns like polite guests at a cosmic dinner party. So as you, noble photon, continue your unending voyage, know this: you're not just fast, you're fundamental. You're the boundary line between what makes sense and what can't be. And for now, that boundary holds strong, like a speed trap written in the stars. You're still cruising as a photon, silent, sharp, and effortless. When another player on the cosmic stage steps out of the shadows, it doesn't shout or sparkle. It doesn't ride on beams of glory or explode in starbursts. It just waits. It is entropy, the quiet accountant of the universe. And if light speed sets the outer limits of motion, entropy handles what happens within those limits, subtly, irreversibly, and always with that smug little shrug. Entropy is the reason your coffee cools, your room gets messy, and your phone charger coils itself into eldritch knots the moment you look away. It is the gentle but relentless push toward disorder. The universe, you'll notice, doesn't tend to tidy itself. Systems evolve from neat and predictable into chaotic and, frankly, uncooperative. But entropy is more than clutter. It's the core of the second law of thermodynamics, which says, in no uncertain terms, that the total entropy of an isolated system can never decrease over time. Translation: you can't unmix cream from coffee, untoast toast, or reverse time without someone raising a deeply suspicious eyebrow. So what does this have to do with the speed of light? Everything. Because while the speed of light defines how fast things can move, entropy helps define why they move at all. Why heat flows from hot to cold. Why stars burn out instead of brightening indefinitely. Why time marches forward and never, ever backward. Imagine watching a movie in reverse. Raindrops leap off puddles, broken vases reassemble, and people politely walk backward into conversations. Physically possible if you just flip the film. But in real life, never happens. That's because entropy always increases. That's the arrow of time, the invisible current pulling us forward and never back. Here's the twist. If something were to exceed the speed of light, it wouldn't just break causality. It would break entropy. It would imply the ability to send information, organized, meaningful patterns, into the past. That violates the fundamental flow of disorder into greater disorder. It's like unburning a candle by yelling at it loudly enough. So now imagine again your hypothetical faster-than-light spaceship. Even if we ignore the energy paradoxes and causal nightmares, entropy would be sitting there in the corner, arms crossed, silently judging you. Because in order for that ship to work, really work, you'd need to decrease entropy along the way. You'd need to make something more ordered than it was before, all while outrunning light. And the universe, it simply does not allow that. Historians still argue whether Ludwig Boltzmann, the 19th century thermodynamics wizard who gave entropy its mathematical teeth, realized he was laying the groundwork for time itself. Some say he was just trying to explain gas behavior. Others argue he understood the philosophical consequences of what he'd found. One fringe rumor even claims Boltzmann predicted the psychological arrow of time, how memory and perception always follow the flow of entropy. That's right, even your thoughts are bound by it. Now back to your photon's perspective. You've been moving since your birth, maybe from a distant star, maybe from someone's microwave popcorn disaster, and you'll keep going until you're absorbed. You never experience time, but from the universe's side, time flows around you. And that flow is steeped in entropy. Every second that passes is another page in the universe's great unwriting, the gradual transformation of structured energy into useless warmth. Which leads to one of the strangest ideas in modern physics. Perhaps entropy, not time, is the real driving force behind change. Maybe we don't experience time moving forward. Maybe we experience entropy increasing and call that time. Light can race through space with no regard for time, but entropy keeps score every step of the way. And here's a quirky tidbit that might gently ruin your next beach vacation. Black holes are the most entropic objects in the universe. One black hole, just sitting there doing nothing in the middle of space, contains more entropy than the entire galaxy around it. That's because it's the ultimate one-way street. Anything that falls in increases the black hole's entropy, and nothing comes out to reverse the process, not even light. Once again, entropy and the light speed limit team up like the world's grumpiest buddy cop duo. And they're not done. Enter information theory, the unexpected cousin to thermodynamics. In this realm, entropy isn't just about heat, it's about knowledge. The more disordered a system is, the less you can predict about it. This connects, somehow unnervingly, to the idea that information cannot travel faster than light. Because information is structure, and structure is order, and order is, you guessed it, the opposite of entropy. So to send information faster than light wouldn't just be a clever trick, it would be a cosmic heist. It would mean packaging order, structure, and meaning into a packet, and launching it into a part of spacetime where it doesn't belong yet. It would be like writing the ending of a mystery novel before the middle has been typed, and then watching the whole plot collapse in protest. Here's another offbeat thought experiment for your pillow tonight. Imagine two observers watching a supernova from different vantage points, one on Earth and one near the explosion. Both will see the light eventually, but each interprets the entropy differently depending on their motion. The arrow of time isn't universal, it's tied to perspective. The universe might be having a lot of different nows, each flowing in one direction thanks to local increases in disorder. This shakes things up, doesn't it? We tend to think of time and speed as objective, but entropy is deeply subjective. It tells your story through your perspective. It's why your ice cream melts while you cry in slow motion on a summer sidewalk. It's why memory can't look forward. And it's why faster-than-light travel remains not just technically difficult, but thermodynamically heretical. So yes, the speed limit matters, but it's entropy that enforces it with ruthless, invisible hands. If the speed of light is the rule carved into the doorframe of reality, entropy is the lock, and the creaky floorboards, and the ghost in the attic that makes sure you never forget where you came from. So you keep moving. Light speed, perfectly timeless, yet never able to go back. You're the ghost of cause and effect, shining forward into an ever-unfolding present. And entropy, it's right behind you, sweeping up the footprints you never made. You're still that glimmer of pure energy, sailing across the void, pressed forever against the fabric of spacetime, while down below in the warm guts of the universe, everything is steadily falling apart. Not in a panicked, chaotic kind of way, but in the quiet, relentless slide that entropy promises, toward disorder, toward stillness, toward equilibrium. It's that slow-motion unraveling that defines everything you are. Because while entropy increases for matter-bound creatures, you, photon, never change. You don't get older, you don't get slower, you don't even get bored. But if entropy is the slow disintegration of order, what gives time its forward tick? Why do we experience events in a line, one after the other, and never in reverse? The answer, once again, involves entropy, specifically its directional bias. This isn't just a metaphor, it's a genuine physical feature of the universe. Every moment we experience feels like the next page in a book, and not the one before it, because the entropy of our surroundings is increasing. We remember the past because it had lower entropy. We can't remember the future because it hasn't had time to get messier yet. This bias, the arrow of time, isn't something built into the equations of fundamental physics. The surprising truth, most physical laws are time-symmetric. They work the same backward and forward. The equations don't care whether time goes up or down the hallway. Newton's laws, Maxwell's equations, even the Schrödinger equation in quantum mechanics, they don't prefer direction. And yet we clearly do. So does your alarm clock, your heartbeat, your entire life. So where does that asymmetry come from? From entropy. More specifically, from initial conditions, namely the bizarrely low entropy state of the universe at the Big Bang. That's the real kicker. The universe started off extremely ordered, a hot, dense, uniform energy soup with fewer wrinkles than a brand new duvet. And from that improbable state, it's been increasing in entropy ever since. Historians still argue whether Ludwig Boltzmann truly appreciated the strange implications of that asymmetry when he scribbled his famous H-theorem in the late 19th century. His math implied that entropy should always increase in a closed system, yet he also realized that the underlying equations didn't seem to care about direction. To resolve this, he proposed something wild. That the forward flow of time is an illusion born of probabilities. Order is simply rarer than disorder, so we remember the rare bits and forget the messy ones. And so here we are. Time isn't a separate force, it's a statistical tendency. You don't fall into tomorrow because of some cosmic push. You fall into it because it's overwhelmingly more likely than falling backward into yesterday. Entropy is the reason why eggs break but don't unbreak. Why you can scramble a Rubik's Cube in seconds, but solving it takes effort, or, if you're like most of us, total surrender. Now here's a fun aside for your inner contrarian. In very small systems, think quantum-level particles, entropy can briefly reverse. That's right. Tiny flickers of decreasing entropy have been observed, like little rebellions against the second law, but only for tiny time scales and tiny scales of energy, like a drop of water jumping back into the faucet before giving up and going down the drain. These reversals are so fleeting and statistically rare that they never scale up. So no, your socks won't fold themselves and your tea won't heat up spontaneously, but for a molecule, maybe, for a millisecond if no one's watching. Meanwhile, you, the photon, remain utterly immune to all of this. You don't have entropy. You don't move forward in time, so you don't experience increasing disorder. You are what happens at the edge of time's arrow, the thing that travels between the ordered and the messy without ever noticing either. You are the straight line in a universe of squiggly ones. And this ties beautifully into your role as a cosmic messenger. Light, in all its forms, is the great communicator of the universe. It moves information. It shows us the past. That starlight you see in the night sky, it left its home thousands or even millions of years ago. Some of those stars aren't even there anymore. You're not looking across space, you're looking through time. But light doesn't get to choose what it shows. It only tells us what was. It can't carry the future because the future hasn't happened. Entropy hasn't increased there yet. And that's another quiet truth the universe doesn't usually say out loud. You can only know things once they've unraveled a little. Once the paint has dried, the dice have landed, the coffee has gone lukewarm. Information flows with entropy, just like time. Even our memories are a record of increasing entropy. Think about it. Your brain stores changes, and changes are asymmetrical. You don't remember a static room. You remember the cup falling, the door slamming, the light flicking off. You're recording entropy's work. You're archiving the disassembly of order moment by moment. So what does this all mean for the speed of light? It means that the limit exists not just because of relativistic constraints, but because any meaningful information transfer, any structured, entropy-carrying signal, can't move faster than light. Not just because it would break causality, but because it would break time's direction. Information would arrive before the system was even disordered enough to create it. You'd be sending memories from the end of the book into pages that haven't been written. That's not just forbidden, it's incoherent. Which brings us to a strange conclusion. Light doesn't just define speed, it defines sequence. It keeps events in order. It's the reason things happen after other things, not before. Entropy sets the flow. Light sets the pace. And so, in the quietest way, the universe protects its story. No skipping ahead, no rewinding, just the forward, gentle slide of increasing disorder, with light carving the path like a cosmic highlighter. A photon travels, yes, but what it really does is remind us that the journey only makes sense if time flows one way, and that things fall apart for a reason. So as you glide on through this strange, expanding universe, timeless, massless, still refusing to buy a watch, remember, you are the edge of time, the courier of entropy, and the one thing that always moves forward, even if you don't. Still zipping through spacetime like a silent, obedient arrow, you, the photon, remain unbothered by the drama of entropy or the geometry of time. But the rest of the universe, it's struggling, especially anything with even a whisper of mass. Because while you get to skim across the cosmos at full throttle, everything else has to slog through it like molasses. And it's not for lack of trying. There's just a hard wall waiting for anything that dares to chase you too closely. This is the mass problem, the why nothing with mass can ever reach light speed problem. And oh, it's a stubborn one. Imagine you're at the gym on a treadmill that tilts up slightly every time you take a step. At first, it's no big deal. You run a little faster, the incline increases a little more. But then something sinister happens. The incline doesn't stop increasing. The faster you go, the more resistance you face. And soon you're sprinting straight up a vertical cliff, and it's still not enough. That's what it's like trying to accelerate a massive object to light speed. Every tiny push forward gets swallowed by the growing energy demands. Add more fuel, get more speed, sure, but less return each time. And when you approach light speed, the energy required to add that last sliver of velocity, just to go from 99.99999% to 100%, is infinite. Not poetic infinite, mathematically infinite. The kind of number that breaks physics and budgets at the same time. This is because of how mass and energy twist into one another when you move fast. Relativity tells us that your mass isn't just your rest mass anymore. As your velocity increases, your relativistic mass increases too. Not because you're physically swelling into some cosmic Michelin man, but because your inertia, the resistance to acceleration, is growing. You're becoming harder and harder to push. Now here's the head scratcher. From your own frame of reference, everything seems fine. You're just cruising along in your spaceship, barely breaking a sweat. But to an outside observer, say, someone watching from Earth, you're dragging an increasingly massive version of yourself through space, and every photon your engines spit out is working overtime just to make a dent. You might think, well, maybe we just need more energy, something better than chemical rockets or fusion. But the universe doesn't care what flavor of propulsion you use. Ion drives, nuclear engines, space sails, it's all the same game. Because this isn't about technology, it's about the underlying rules of spacetime. And those rules say, if you have mass, you will never ever reach the speed of light. Historians still argue whether early 20th century physicists really grasped the magnitude of that limit when Einstein first proposed it. Many assumed at the time that it was just a practical issue, a kind of temporary roadblock we'd eventually engineer our way around. It wasn't until particle accelerators, those enormous metal donuts of scientific ambition, came along that the truth hit home. No matter how hard you push a particle, no matter how many giga-electron volts you throw at it, it only gets closer to light speed. Never there, never beyond. Take the Large Hadron Collider, for example. It can accelerate protons to 99.999999% the speed of light. At that point, The proton's mass is more than 7,000 times its rest mass. It's essentially a tiny bowling ball with the energy of a freight train, flying in circles under the Swiss countryside. But even then, it's still slower than a photon. Always. And that tiny gap, the space between almost and exact, is where physics plants its flag, because that's the line between what's possible and what's not. Not because of engineering or imagination or ambition, but because of what mass is. It anchors you. It tethers you to time and space in a way that light simply is. Which brings us to the awkward cousin in the family, the neutrino, a ghostly little particle that almost behaves like light. It has a teeny tiny mass, travels just under light speed, and barely interacts with matter. Billions of them are flying through your body every second, and you wouldn't even know unless they bought you dinner first. For years, people thought neutrinos might actually be massless, just like photons. But the discovery of neutrino oscillation, meaning they can change flavor as they move, proved they must have mass. Which means, yep, still not allowed to travel at light speed. You'd think that would be discouraging, and maybe it is if you're trying to engineer a warp engine out of chewing gum and optimism. But there's something elegant about this limit. The more mass you have, the more deeply embedded you are in time. The more you resist acceleration, the more you experience the passage of moments. Light doesn't get to age, but you're soaking in time. You're living in it. And that's a strange, beautiful trade-off. Mass slows you down, but it also lets you participate in the unfolding story of the universe. It lets you remember things, plan things, feel cold, and listen to music. Light can't do any of that. It just moves forward, timeless and unknowing. Here's a quirky historical tidbit to stick in your pocket. In the 1920s, there were serious debates about whether electrons had some kind of internal structure. A mass engine that somehow rotated or vibrated fast enough to give rise to inertia. These ideas didn't hold up, but they reflect a deeper curiosity. What is mass, really? We still don't fully know. The Higgs mechanism explains how particles acquire mass, but it doesn't fully explain why that mass has the exact value it does, or why adding mass should prohibit light speed travel so thoroughly. That remains one of modern physics' most pressing mysteries, folded neatly into a set of constants that the universe just shrugs and hands us. So no, you can't chase light as a massive object. Not ever. You can get close enough for time to stretch and warp, close enough to see your reflection in the bending of space. But the finish line always recedes. You'll never catch up. And yet, paradoxically, this inescapable boundary is what shapes the cosmos. Stars burn, planets orbit, atoms stay put, all because mass has limits and light defines them. Every interaction, every force, every push and pull unfolds in the shadow of a rule that says, you may not pass. So you continue, dear photon, weightless, limitless, unaware. You don't struggle, you don't stretch. You don't change. You are the perfect traveler in a universe that can only dream of your speed. But for everyone else, every object with mass, the journey is slower, full of friction and time and the beautiful gravity of limitation. You glide onward unchanged, undisturbed, and utterly indifferent to the ticking clocks of the universe. But down on Earth, clocks do tick. They measure something you'll never feel, duration. And that duration, that steady rhythm of past into present into future, holds strange secrets once we put two humans through a little experiment. Or rather, a thought experiment. Because tonight, we're dragging you into one of physics' most iconic mind-benders, the twin paradox. Don't worry, you're still a photon. But we need you to spectate for this one. Picture it like a play, two identical twins, earthbound and bright-eyed. Let's call them Lena and Cass. Lena stays home, makes banana bread, lives a normal life with normal gravity. Cass, on the other hand, hops aboard a near light-speed spaceship and zips off into space for a while. Maybe she's got errands on Alpha Centauri. Doesn't matter. She travels at a significant fraction of light speed, turns around, and comes back. And when she does, Lena's got gray hairs and a new hobby in birdwatching. Cass, meanwhile, steps off the ship looking, well, barely older than when she left. Maybe a light wrinkle, skin glowing, some light-speed skin care, possibly, but no creams or serums, just time dilation. Now here's the kicker. To both sisters, time felt normal. Lena aged normally on Earth. Cass, in her spaceship, also felt like time passed at the usual pace. She read books, took naps, listened to the same podcasts we all lie about finishing. But when they reunited, Lena had lived significantly more time than Cass. And this isn't a poetic metaphor, it's a literal outcome predicted and confirmed by special relativity. Because as Cass approached the speed of light, her internal clock slowed down compared to her sister. From Earth's perspective, her journey took years. But on the ship, maybe only months. Her biological processes, heartbeats, thoughts, fingernail growth, slowed right along with that clock. Not in some creepy sci-fi stasis way, but in a very real, very verified way. Time itself warped around her. This isn't just theory. We've run experiments that mirror this. Atomic clocks flown on airplanes tick slightly slower than their synchronized counterparts left on Earth. Muons, those unstable particles we mentioned earlier, decay slower when moving fast. We've seen this effect, measured it, confirmed it. Cass could absolutely come back younger and no one could sue her for it. Historians still argue whether Einstein himself truly expected this level of weirdness when he proposed time dilation. Some early critics thought it was absurd, impossible even. But by the 1970s, with high-precision clocks and high-altitude flights, the data was irrefutable. Time isn't fixed, it flexes, it bends. And the closer you get to light speed, the more it cooperates with your refusal to age. Of course, there's a catch, isn't there always? The paradox, part of the twin paradox, comes from confusion about symmetry. After all, shouldn't Cass see Lena's clock moving slow too? From Cass's point of view, is she the one at rest and Lena the one moving? It seems like each should see the other aging slowly, like a cosmic mutual misunderstanding. But here, where the asymmetry sneaks in, acceleration, Cass had to turn her ship around. That means she changed direction. She experienced forces that Lena didn't. And even in special relativity, acceleration breaks symmetry. It marks Cass as the one who switched frames. Her journey isn't a straight line through spacetime, it's a boomerang. And that makes all the difference. And here, where things get deeply cozy in their weirdness, the more Cass pushed toward light speed, the greater the difference in aging would be. At 90% light speed, time dilation is noticeable. At 99.99%, it's dramatic. At 99.9999999%, it's staggering. A 10-year journey for Lena might feel like mere hours for Cass. It's not just a delay, it's a full rescheduling of existence. Now pause for a moment and think about what that means. Not in math terms, in human terms. It means you could travel into the future simply by accelerating. You could skip ahead while the rest of the world unfolds at its usual pace. Friends age, technologies evolve, empires rise and fall. Meanwhile, you experience a compressed slice of life in a metal can at relativistic speeds. It's time travel, kind of, just in one direction and with no rewind button. But remember, the closer you get to light speed, the more impossible it becomes to reach it, because you're carrying mass. And the universe charges a steep toll for speed. That's what keeps you from becoming a photon yourself. You might age slower, but you'll never stop aging entirely. The light speed barrier still holds. Here's a quirky tidbit to keep in your mental back pocket. In 1971, two physicists, Haefel and Keating, flew atomic clocks around the world in commercial jets. When the clocks were reunited with their stay-at-home cousins, the ones that had flown were slightly behind, by a few nanoseconds. The effect was tiny, yes, but exactly what relativity predicted. They literally watched time bend with speed. Kaz, of course, would see far more dramatic effects. Her journey becomes a way to stretch and contract the flow of time like taffy, simply by choosing how fast and how far she travels. And as strange as that is, the math makes it all beautifully consistent. No contradictions, no paradoxes that break the universe, just the elastic fabric of spacetime doing its thing. And yet you, the photon, experience none of this. No matter how dramatic Cass's trip was, she still aged. She still experienced time, just more slowly. But you don't age at all. You don't have a timeline. You're emitted, you're absorbed, and the entire journey feels like a single dot in the spacetime ledger. Which means, oddly enough, that the closer Cass gets to being like you, the less she gets to experience. Relativity rewards speed with time savings, but at the cost of living. You trade days for distance, seconds for miles. The closer you move to light speed, the more you hollow out the experience of moving. That's the irony. Cass comes back younger, but she's also missed out. She skipped the world's unfolding moments. And though she's defied age, she hasn't escaped consequence. So as you zoom forward, eternally immune to these timelines, you also sit outside of the human story. You're the yardstick we all compare against, but you don't remember the measurement. You don't remember anything. That's the price of perfect speed, the absence of everything else. Still no rest, no pause, no ticking seconds for you, photon. You sail across spacetime at the cosmic speed limit, the fastest anything can move without shredding the script of the universe. But how does the universe know what that limit is? Who's holding the radar gun? Who says, "Whoa, slow down, no faster than that"? The answer, surprisingly, isn't about the particles themselves. It's about the stage they're moving on. Because if you want to understand why there's a speed cap, you have to stop thinking about objects and start thinking about spacetime. Now picture this. Spacetime isn't just an empty backdrop. It's not a bland theater curtain behind the action. It's the set, the script, the director, and the lighting guy all rolled into one. And baked into its geometry, woven into its very angles and proportions, is the ultimate speed limit, the speed of light. Not because light is special, though you are, don't get cocky, but because light speed emerges naturally from how space and time are connected. Let's break it down gently. In special relativity, spacetime is modeled as a four-dimensional continuum. 3 dimensions of space, up, down, left, right, forward, back, and one of time. These aren't separate ingredients, they're part of the same batter. Move in space and you affect how you move through time. The faster you go spatially, the slower you move temporally. You trade one for the other, and there's only so much to go around. Here, where it gets elegant, every object travels through spacetime at a constant rate, known as its spacetime interval. Even when you're sitting perfectly still on the couch, binge-watching old documentaries and pretending it's research, you're still moving through time. That movement, through the time axis, is your full velocity in spacetime. You're traveling at the speed of light, just entirely in the time direction. But as you begin to move through space, walk, run, launch yourself into orbit, you start tilting your motion away from the time axis. You borrow from your time movement to make room for space movement. The faster you go through space, the less you move through time. And once you hit light speed, you've gone all in on space. 0 time left. You're moving fully across space and not at all through time. That's you, photon. This rule isn't enforced by some intergalactic traffic cop. It's baked into the Pythagorean structure of spacetime itself. You can't move faster than light because that would require you to move through spacetime faster than spacetime allows. And spacetime is very strict about its math. Historians still debate whether the concept of a fixed spacetime interval was fully appreciated when Einstein first published his work in 1905. Minkowski, a mathematician who refined Einstein's ideas a few years later, is often credited with making the whole idea of four-dimensional spacetime geometrically coherent. In fact, Minkowski once described time and space as doomed to fade away into mere shadows, unless united into a single concept, spacetime. A little dramatic, sure, but he was right. And this geometric view gives us a powerful insight. The speed of light isn't about how fast light moves. It's about the structure of spacetime itself. Light is just the thing that happens to move at that speed. It's not setting the limit, it's riding the wave. Here's a metaphor to ease the brain tension. Imagine spacetime as a sheet of paper. Light speed movement is like tracing the edge of the sheet, a line tilted perfectly between the space and time axes. Any other movement falls within that tilt, faster than light. That would mean drawing outside the sheet, where there's no geometry left to describe what's happening. You'd be asking for coordinates where the system doesn't have coordinates. It's not just illegal, it's undefined. This isn't a philosophical quirk, it's a hard boundary in the math. The Lorentz transformations, the equations that govern how different observers in motion perceive space and time, break down at light speed. Try plugging in a speed greater than light and suddenly you're getting square roots of negative numbers where there shouldn't be any. Congratulations, you've just invented an imaginary distance. Not fantastical imaginary as in square one. It's the math's way of saying, yeah, that's not a thing. Let's toss in a quirky historical tidbit here. When Einstein first proposed that the speed of light was constant in all frames of reference, people thought it was either a genius revelation or complete nonsense. Some believed it implied that the ether, the hypothetical invisible medium light was supposed to travel through, must have magical properties. Others realized, slowly and painfully, that the ether wasn't needed at all. Light didn't care about any medium. Its speed was built into the geometry of the universe. And that's a shift that took decades to fully sink in. For centuries, physics had treated space and time as separate, absolute containers. Space was just where things happened, and time was when things happened. Einstein and Minkowski shattered that simplicity. Now, how fast something moves, and whether it experiences more space or more time, is all part of a single, unified structure. What does that mean for you, dear photon? It means you're the purest possible expression of motion through space. You are the boundary line on every light cone, the edge of what's causally connected. You're not pushing against spacetime. You are what spacetime allows. This also explains a very curious feature of relativity. No observer can ever see something moving faster than light, not even if you try to chase it. No matter how fast you go, light always stays just ahead of you at exactly the same speed. It's like running toward a mirage. It never gets closer, never further, just stubbornly constant. Because it's not about your speed relative to the light. It's about the invariance of spacetime geometry. From every vantage point, the light speed barrier is in the same spot. So whether you're a planet, a spaceship, a neutrino, or a very determined house cat launched into orbit, don't ask. You'll always be bound by that speed. Because that speed isn't an option, it's a dimension. And dimensions don't negotiate. Now zoom back out. Light speed isn't some speed limit set on a whim. It's a fundamental feature of how space and time relate. It defines what's possible and what's not, what's visible and what's forever disconnected. It draws the edges around every moment, every signal, every beam and burst. And you, photon, race along that edge, the perfect traveler in a universe held together by rules so elegant, they feel invisible until you try to break them. You're still gliding through space-time, motion without mass, speed without effort. You are the standard, the yardstick, the cosmic benchmark against which all motion is measured. But let's talk about that for a moment. Because it turns out, you don't just move at the speed limit, you define it. You are the ruler and the ruled. The limit isn't just about you. It's the very boundary of how information, influence, and even causality travel through the cosmos. The speed of light isn't a nice-to-have rule. It's more like a space-time traffic law, a universal, unbreakable speed regulation carved right into the structure of reality. Imagine a universe with no speed limit. Sounds fun, right? Infinite shortcuts, intergalactic pizza deliveries in under a second. But peel back the fantasy and things get ugly. Without a speed limit, you could send signals faster than light, create causality violations, and break down the very principle that makes time. Well, time. Things could happen before their causes. Fires could light before matches are struck. Punchlines could arrive before jokes. It would be chaos. Not the fun, movie trailer kind, but the irreversible, brain-melting kind. So how does the universe enforce this? Not with flashing lights or red and blue sirens, but with the geometry of spacetime itself. You remember those light cones from earlier? They're the visual metaphor for this law. Every event in spacetime creates a cone, one pointing forward in time future, one backward past. The cone's surface, that's your home, photon. Anything inside the cone can be influenced by or can influence the event. Anything outside, off limits, no connection, no influence. The cone is causality's fence. And here's the catch. Nothing outside that cone can ever catch up. No information can leak beyond it. It's not just a limit on speed. It's a limit on effect. If you're outside someone's light cone, your paths through spacetime are causally disconnected. It's not that your message would be late. It literally could not arrive. This structure means you can map out every possible future influence for any point in space and time. Your grandmother's birthday, a solar flare, a missed bus, each sits somewhere within or outside of the light cone of your current moment. If it's outside, it's irrelevant to you for now. Only light speed or slower can bring it in. That's why this speed limit is more than a number. It's a way of preserving consistency. If the speed of light weren't the universal ceiling, if there were even a whisper of a loophole, then all of physics would begin to unravel. Quantum fields would get messy. Thermodynamics would roll its eyes and walk out. The very concept of an observer would stop making sense. Historians still debate whether the earliest adopters of relativity grasped just how radical this idea was. Einstein may have seen it in his equations, but others, especially in the first half of the 20th century, were still clinging to Newtonian intuitions. Some scientists resisted, argued, even ridiculed the notion that there could be a built-in limit to how fast a thing could go. But experiment after experiment, light speed held, always the same. No matter who measured it, no matter how fast they were moving. It's like measuring the speed of sound and always getting the same number, even if you're the one shouting into the void from a bullet train. This brings us to something weird. If every observer, no matter how fast they're moving, measures the speed of light as the same, what gives? Shouldn't someone chasing after a photon see it moving slower? Nope. Because spacetime distorts to make it true. Length contracts, time dilates, mass inflates. Everything warps around that one sacred number, so it remains constant no matter what. That's not a speed, that's a shrine. And it's not just photons playing by these rules. Every field, every particle, every interaction in the universe, gravitational, electromagnetic, nuclear, is tethered to this same limit. Even gravity, which Einstein would later describe not as a force but as a curvature in spacetime, obeys the speed of light. Ripples in gravity, gravitational waves, propagate at exactly light speed. No faster, no cheating. It's like every phenomenon in the universe got the same memo. Maximum speed equals c violators will be deleted from causality. Now let's get a little quirky here. What if someone almost broke the rule? Not faster than light, but really, really close, like within a decimal sneeze. We see this all the time in particle accelerators. Electrons and protons accelerated to 99.999999% of light speed. From their frame time crawls, length contracts, they are nearly frozen in motion, but they still can't reach the limit. That last sliver of speed becomes a wall of infinite resistance. Think of it like trying to physically touch the end of a rainbow. You chase it, you close in, but the closer you get, the further it shifts. The universe doesn't just say no, it laughs softly and turns up the math. And so the cosmic traffic law holds, not out of stubbornness, not because of some godlike edict, but because that's how spacetime is built. It's as natural as a triangle having 180 degrees. You don't argue with geometry, not when the entire universe agrees on the rulebook. Let's not forget the humans in this story. Our satellites, GPS systems, and even your smartphone navigation apps rely on this law. If light didn't travel at a known constant speed, your location would be off by kilometers. Communication between Mars rovers and Earth, timed by light speed. Astronomical observations, based on how long it takes light to reach us. It's the metronome of cosmic measurement. So here you are, photon, still gliding effortlessly along the edge of the cone. You don't age, you don't wait, you don't even glance back. You are the messenger, the limit, the law, all in one. The rest of the universe may strain and struggle, but you're already there. You're still coasting, if we can even call it that, when motion loses all meaning at your level, along the pure edge of spacetime, massless, ageless, and tireless. And while your journey looks like smooth sailing through empty space, that empty part, that's where things get sneaky. Because space, as it turns out, is never truly empty. Even when stripped of all matter, all gas, all dust and radiation, the vacuum itself remains restless. A fizzing, jittering sea of quantum whispers. And guess what? It messes with you too. Let's pause and reset expectations. A vacuum in the classical sense is supposed to be nothing. No particles, no waves, no movement. Just blank, silent void. But quantum mechanics laughed at that concept a long time ago and promptly smashed it into glitter. According to quantum field theory, even empty space is bubbling with activity. Fluctuating fields, popping particle-antiparticle pairs, virtual blips of existence that wink in and out faster than anyone can track. You, dear photon, are trying to cruise through this party like a ghost, but the dance floor keeps shifting. These fluctuations create a kind of texture in the vacuum, like running your hand across what looked like a polished table only to realize it's slightly sticky with mystery sauce. And this quantum restlessness isn't just abstract mumbo-jumbo. It has measurable effects. For instance, the Casimir effect, a fringe-sounding phenomenon that's very real. Place two uncharged metal plates extremely close together in a vacuum, and they attract each other. Why? Because the vacuum between them has slightly fewer allowed quantum modes than the space outside. Translation: the plates are pushed together by the vacuum itself. Let that sink in. Nothing is doing something. Now, how does this pertain to you, photon? You might be flying through what we call a vacuum, but you're not really alone. You're weaving your way through a jittery field of fluctuating energy, one that imposes subtle limits and influences on your behavior. This vacuum energy interacts with you, just a bit, creating slight shifts in your path, your polarization, even your effective speed when passing through certain media. Yes, your speed is affected depending on the environment. In a perfect vacuum, your speed is still c, the universal constant. But when you travel through materials, glass, water, air, you slow down, slightly. This is not because you decide to take it easy, but because you're constantly being absorbed and re-emitted by the atoms in your way. It's a stutter step, not a glide. This is why, for example, light bends when it moves from air to water. That bending, Refraction isn't just a fun trick for spoons in a glass. It's a sign that light is interacting with the medium's structure. And while you might think, oh, that's just materials, not the vacuum, here's the plot twist. The vacuum has structure too. Enter vacuum polarization, another term that sounds like a band no one listens to but is actually central to modern physics. It describes how the presence of a particle, like an electron, can distort the vacuum around it. The vacuum isn't passive, it reacts. It's like tossing a rock into a still pond, only the ripples are virtual particles and the pond is spacetime. Historians still argue whether Paul Dirac, the 20th century physicist who proposed the existence of antimatter, fully appreciated the consequences of this sea of particles within the vacuum. He introduced the idea of a vacuum filled with negative energy states, what later got reinterpreted as the fluctuating quantum vacuum. Some say he saw the tip of the iceberg. Others believe he quietly opened the door to a concept so wild, we're still unpacking it today. Now here's where it gets even weirder. These vacuum fluctuations have an energy density, tiny but non-zero. And when we add up all the quantum fields across all of spacetime, we get something astonishingly large, the vacuum energy problem. According to quantum theory, the vacuum should have a vast amount of energy. But when we look at the real universe, its expansion and acceleration tell us the energy is far smaller, off by 120 orders of magnitude. This isn't just a wrong answer. It's the most wrong answer in all of physics. And yet, even wrong answers have consequences. That discrepancy might be tied to dark energy, the mysterious force that's causing the universe to expand faster over time. Some physicists suspect that vacuum fluctuations are playing a part, stretching the universe subtly, persistently. Imagine a restless sheet of fabric slowly unrolling in every direction, powered by the background murmur of space itself. Which means, photon, that your straight-line journey might be a little less straight than we thought. You're not traveling across static, flat terrain. You're surfing across a dynamic, fluctuating foam. Quantum foam, if you like your metaphors bubbly. Every meter you cross is buzzing with virtual activity. You can't feel it. You don't care. But it shapes the environment you travel through nonetheless. Here's a fun, fringe tidbit. Some physicists have speculated that this quantum foam could cause tiny, random deviations in your path over cosmological distances. If true, distant starlight might arrive on Earth with the tiniest amount of quantum jitter, not enough to ruin the image, but enough to nudge us toward the edges of measurable physics. There are entire observatories tuned to catch these possible blips. So far, no clear signals. But still, space may not be as silent as it seems. So while you, photon, are always moving at sea in the vacuum itself is a tricky place. It's not a passive backdrop. It's an arena, a sea, a whispering field of probabilities and temporary somethings. And while you may not interact with it in the messy way massive particles do, you still surf its currents. You travel as light, yes, but light doesn't move through spacetime, it moves with it, bound to its structure, shaped by its foam, whispered to by the vacuum beneath your wings. And so you glide on, never slower, never older, but not untouched. You are the line on the chalkboard, drawn across a surface that's never fully still. Still locked into your timeless streak through the jittery vacuum, you, our ever-stoic photon, have managed to dodge everything from mass to minutes to metaphysical meltdowns. But now, we need to talk about the forbidden fruit of physics, the ultimate cosmic temptation. The what-if that dangles like an irresistible cheat code in a video game made of gravity and algebra. What if something actually could go faster than light? Let's imagine it, not almost light speed, not 99.9999%, but faster, past the barrier. Beyond C, you'd think the universe might just throw up its hands and let it happen, maybe even hand out a prize. But no, crossing that line doesn't just break a few physics laws, it breaks everything. Like, genuinely everything. Time, cause, and effect, the direction of history, your entire understanding of what before and after mean. All of it collapses like a souffle under a jackhammer. See, the speed of light isn't just about motion. It's the speed of causality. That's the key. It's the speed at which information can travel. And if you could send information faster than that, like, say, a message to your past self warning not to microwave fish at the office, you'd create a causal loop. That's where the problems begin. Let's say you send a signal faster than light to your friend on another planet. She gets the message before you hit send, thanks to how time and simultaneity behave at relativistic speeds. She reacts, does something that prevents you from sending the message in the first place. And suddenly, we're knee-deep in a grandfather paradox. No cause, no effect. Or worse, effect then cause. The sequence unravels. This isn't just a philosophical headache, it's a physical one. Special relativity is built on the idea that the laws of physics are the same in all inertial frames. But allowing faster-than-light signals means there exists some frame in which time reverses. Events unhappen. Fire unburns. Cats become uncurious. Reality doesn't just twist, it tears. So naturally, physicists have spent way too much time trying to find a way around this without actually violating the laws. Enter hypothetical particles known as tachyons. These ghostly creatures would always move faster than light. Not sometimes, always. They can't slow down to light speed any more than a photon, can slow down at all. They'd have imaginary mass and their energy would decrease as their speed increased. That's right. The faster they go, the less energy they carry. It's the upside down of particle physics. Tachyons are, to be blunt, theoretical mischief. They were proposed to test the limits of what relativity could handle, not because anyone had seen one sneak through a detector. And no, despite what fringe internet forums and that one weird dream you had in 2009 may claim, we haven't observed them. Not once. No trails, no blips, no interactions. But they still haunt the footnotes of physics papers, lingering like that unpaid parking ticket you keep pretending isn't real. Now if tachyons did exist, and that's a cosmic-sized if, they could, in theory, send information backward in time. And that alone is enough to raise every red flag in the logical universe. Because information isn't just data, it's structure, it's order. And as we've already seen, sending order backward in time would reduce entropy. You'd be cramming more order into the past than it had originally. You'd be revering the arrow of time. That, friends, is a big no-no. Historians still argue whether faster-than-light ideas were ever taken seriously at the foundational level. Some early 20th century physicists considered them curious thought experiments, like a cat playing chess. Impressive, but not really dangerous. Others warned that even entertaining such notions could lead to violations of causality and paradoxes that would destabilize entire frameworks. Today, most physicists view tachyons as mathematical artifacts, useful in certain quantum field theories, but not likely to exist in the tangible universe. But the itch never goes away. In science fiction, and sometimes even in serious theoretical corners, the fantasy of faster-than-light persists. Time machines, warp drives, hyperspace lanes. We are drawn to it, because if you could go faster than light, you could go anywhere. The galaxy becomes local, distances collapse, time becomes pliable. You could witness the birth of stars, or go back to watch yourself awkwardly hug someone who was clearly going in for a handshake. Still, you, our tireless photon, are unaffected by this speculation. You travel at light speed, not above it. You are the ceiling. And because of that, your movement preserves cause and effect. You never arrive before you're sent. You never deliver a message before it's written. Your path may be strange, but it's consistent. Your obedience to the limit is what keeps the fabric of reality stitched together. And you're not alone in this. All massless particles, gravitons if they exist, or gluons in a perfect vacuum, are similarly bound. They travel at light speed, not beyond. They define the cone of influence around every event. The universe is built on these constraints. They are not weaknesses, they are strengths, safety features, guardrails. Here's a fringe but fun example. In quantum entanglement, particles seem to communicate instantaneously, no matter how far apart. This feels like a faster-than-light cheat, but entanglement doesn't actually send information. It's correlation, not communication. No usable data crosses the divide at superluminal speed, so causality is preserved. Einstein called it spooky action at a distance, and he didn't mean that as a compliment. But even the spookiest actions never violate the ultimate speed limit. So we come back to the truth. Anything faster than light, truly, measurably faster, would destroy the logical structure of physics. It would break our most fundamental symmetry, the idea that time flows in one direction and that effects follow causes. Without that, reality turns to soup. So no, there are no real faster-than-light particles. Not yet, maybe not ever, and that's probably for the best. The light speed limit isn't an inconvenience, it's a firewall. It protects the coherence of existence. It keeps everything in the right order. The fall before the bruise, the joke before the laugh, the light before the shadow. And you, photon, obey it without effort. You travel exactly as fast as you must. No more, no less. You are the trusted courier of the universe, never early, never late, always arriving exactly when causality demands. You're still soaring, if soaring even makes sense when you don't perceive motion, time, or change. A beam of pure determination, threading through spacetime like a needle that doesn't remember piercing the fabric. And while you've escaped gravity, aging, and all those pesky concepts tied to mass, there's one place you wouldn't escape from, not even with all your light speed finesse: the edge of a black hole. Ah yes, the event horizon, the cosmic do not return line, the place where even you, swiftest of the swift, meet your match. Because as it turns out, the speed of light isn't just a speed limit, it's also a wall. And black holes, they are what happens when that wall gets twisted inward, folding spacetime until it traps even light itself. Let's set the scene. Picture a star, massive and wild, reaching the end of its fusion-fueled life. It collapses, not with a bang, but with a crunch. Its core implodes under the weight of its own gravity. And if it's massive enough, no known force can stop the collapse. The star becomes infinitely dense, a singularity, surrounded by a boundary so extreme that nothing, not even you, dear photon, can escape once crossed. From the outside, this boundary is the event horizon, and it's not some hard surface. It's just the last coordinate where escape is still mathematically possible. Beyond it, spacetime curves so steeply inward that all paths, even those taken at light speed, lead only further in. It's not that you're slowed down. It's that every direction, even outward, now points inward. Think of it like this: you're skating on a funnel-shaped ramp. At first you glide along the rim, then you spiral downward. At a certain point, no matter how fast you skate, gravity curves the ramp so steeply that there's no way out. You fall. Light falls. Causality folds in on itself. And time starts doing things that would get it kicked out of respectable physics clubs. From an external observer's point of view, something falling into a black hole appears to slow down as it nears the event horizon. Slower and slower until it seems frozen in time, never quite crossing the boundary. But from your point of view, riding the photon into oblivion, it's instant. You zip in without noticing anything special at all. No signs, no warnings, just more space and then less. Inside the event horizon, space and time effectively switch roles. Time becomes a direction you can't escape. Forward in time now means inward toward the singularity. You don't fall into a black hole. You fall through time toward the most compact future imaginable. Once you've passed that horizon, everything you experience leads to one conclusion: the center. Historians still debate whether Einstein, when he developed general relativity in 1915, fully imagined black holes in their modern form. The mathematics was there, hidden in Karl Schwarzschild's solution to Einstein's equations, sent from the trenches of World War I, no less. But the implications were so extreme that even Einstein himself doubted their physical reality, a place where time stops, where light itself can't escape. It sounded like math gone rogue. But then came the evidence. Indirect at first, strange stellar orbits, bursts of radiation, and finally, in 2019, the now famous image, a glowing ring around a dark center. The Event Horizon Telescope had captured the shadow of a black hole. Not a cartoon, not a simulation, a real photo of something that bent light so completely that we saw the absence of escape itself. And yes, that image was shaped by light like you, photons tracing curved paths around a singularity, some circling once before flying off to tell the tale, others doomed to spiral in forever. Black holes don't reflect light. They don't glow. What we see is the light that just barely avoided capture. Now here's the twist. The speed of light still rules inside a black hole. Even at the edge of physical comprehension, the laws don't break. They just get weird. The light speed limit isn't violated. It's obeyed so strictly that the entire spacetime within a black hole becomes a one-way street leading to the singularity. It's not that you're moving faster than light. It's that the geometry itself leaves no paths that lead outward. Let that sink in. The speed of light remains the universal speed limit, even in a place where light can't escape. That's how deep this rule runs. It doesn't just govern motion, it sculpts the landscape. When the spacetime terrain tilts far enough, even you, eternal photon, are pulled in, not because you've slowed down, but because all possible paths at your speed point inward. Here's a deliciously quirky tidbit. There's a region just outside the event horizon called the photon sphere, a place where light can orbit a black hole in unstable loops. That's right. You can technically orbit a black hole. Not indefinitely. Your path will decay eventually. But for a few whirling moments, you can circle the drain of the universe, like a fly around the mouth of a giant, invisible bottle. It's within these photon spheres that light can create incredible visual distortions. Rings, echoes, mirages of stars behind the black hole, bent into halos by extreme gravitational lensing. You're not just a traveler here. You're an artist, painting the warped sky with illusions born from the strict obedience to spacetime curvature. And then there's Hawking radiation. Stephen Hawking's stunning 1974 proposal that black holes aren't completely black. Due to quantum effects near the event horizon, pairs of virtual particles can pop into existence. One falls in, the other escapes, stealing a little energy from the black hole. Over time, this could cause the black hole to evaporate, photon by photon, until nothing remains. It's a poetic fate, the ultimate trap slowly leaking away its secrets at the speed of light. So here's what we've learned. Even in the darkest corners of the universe, where gravity crushes and space collapses, the speed limit still holds. Light doesn't break the rules, it's guided by them. Spacetime doesn't rebel, it just folds the rules until they become inescapable. And you, photon, remain true. You don't hesitate at the edge of a black hole, you don't question it. You simply follow the path spacetime lays out for you. And if that path bends inward forever, then so be it. No drama, no defiance, just motion. But for the rest of us, those with mass, those bound to time, the existence of black holes is a chilling reminder that light speed doesn't just define how fast we can go. It defines where we can go. And once space curves enough, even the fastest among us have no escape. Still moving at your unbeatable pace, unflinching, unaffected by time or traffic or existential dread, you, our trusty photon, might be forgiven for thinking you've seen it all. You've skirted black holes, woven through quantum foam, survived philosophical paradoxes. Surely now your throne as the fastest thing in the cosmos is secure, right? Well, not quite, because there's one scenario, just one, where something with mass does go faster than light. It's not in a vacuum and it's not breaking the cosmic speed limit, but it is bending it. And you've probably seen it before. It glows an eerie electric blue like a ghost caught mid-scream inside a nuclear reactor. It's called Cherenkov radiation. Let's set the stage. Imagine a charged particle, say an electron, blasting through a medium like water. It's moving faster than light can move in that medium. Not faster than you in your vacuum-modeled perfection, but faster than the local speed of light in water, which is about 75% of your usual speed. And when that happens, boom, the particle emits a shockwave of light, a glow, a beautiful bluish burst of surrender. That's Cherenkov radiation. To understand it, let's go sonic for a second. You've heard of sonic booms, those sharp cracks produced when something moves faster than sound. The object outruns its own sound waves, piling them up into a shock front. Cherenkov radiation is the optical equivalent. The particle outruns its own electromagnetic disturbance, creating a conical burst of light, like a ripple chasing an invisible speedboat through space-time. Now you, the ever-pure photon, don't break this rule. You're still moving at light speed in your medium. You don't slow down, the medium makes you take detours. You're absorbed, re-emitted, nudged, refracted. That's why your effective speed drops in water or glass. Meanwhile, our little electron skips past you, vaulting ahead, not in vacuum but in matter. It's not disobeying physics, it's exploiting a local rule, a technicality. And that's the key. Cherenkov radiation doesn't violate the universal speed limit. The electron isn't going faster than you in your natural vacuum environment. It's just going faster than light in that specific material. The law still holds. The universe doesn't blink. Still, the result is spectacular. Nuclear reactors submerged in water glow with this uncanny light. It hums with silent menace. A reminder that something unnatural is happening, even if the math checks out. You've seen the blue glow in science documentaries, maybe even in video games, but now you know. That's light's own version of a sonic boom, a ghost trail of particles daring to outpace their local speed limit. And this glow has practical uses too. Cherenkov detectors are deployed in neutrino observatories, deep underground or submerged in pure water tanks. When a neutrino smashes into an atom and knocks out a high-speed particle, that particle can emit Cherenkov radiation. We see the glow and infer the collision. The light betrays what the neutrino tried to do in secret. Historians still argue whether Pavel Cherenkov, the Soviet physicist who first observed this radiation in the 1930s, realized the full scope of what he had uncovered. Some accounts suggest he thought it was merely a background effect, a visual quirk. It wasn't until later, with the help of Igor Tam and Ilya Frank, that the phenomenon was properly explained. And for their work, all three earned a Nobel Prize. Not bad for chasing ghosts in a bottle. But this phenomenon also underscores a deeper idea. The speed of light isn't one number everywhere always. The value C, 299, 792, 458 meters per second, is the speed of light in a vacuum. In any material, light slows down. Slightly in air, more in glass, even more in water. But the ultimate limit, the thing that defines causality and makes your path through space-time possible, is always C in vacuum. That's the real ceiling. Everything else is just terrain. Let's take a moment to marvel at the particle pulling this stunt. The electron is tiny, but it has mass. It's not supposed to win in a race against light. But by jumping into a denser medium, it exploits your delay, your repeated interactions with the atoms of water, and surges ahead just long enough to generate that signature glow. Then it slows. The radiation saps its energy. The shock front fades. Balance is restored. It's a brief, glorious moment of almost cheating. And that idea of context-dependent speed comes up in other weird places too. In metamaterials, for instance, researchers can slow light dramatically, even to a crawl. They manipulate the structure of materials at the nanoscale, guiding light through complex paths that stretch its journey out in space and time. In a lab, light can be made to pause inside a specially tuned crystal or gas. Not truly stopped, because again, you can't actually trap a photon like a hamster, but delayed, redirected. It's like making a maze for light and watching it get politely lost. Even more surreal, there are materials with negative refractive indices. In these, light bends the wrong way. It refracts on the other side of the normal. And while this doesn't make you move faster, it does make your path weirder, stranger. Light manipulated into loops, traps, illusions. Welcome to the optical funhouse. So here, where we are. Yes, something with mass can move faster than light in a medium, but never faster than light in vacuum. The global speed limit remains sacred. What Cherenkov radiation reveals is not a rule broken, but a rule revealed. A moment when physics pulls back the curtain and says, here's how tight the math really is. And you, dear photon, are still at peace. You don't need to race through water. You don't envy the electrons. You take the path the medium allows you to take, never faster, never slower than permitted by the laws you helped define. You don't cause Cherenkov radiation. You witness it, like a boundary being nudged but never crossed. And when it fades, when the glow settles back into the calm of normal physics, you continue your path unchanged. Still light, still law-abiding, still moving at the pace that holds the universe together. You've seen a lot for a massless beam of energy, flirted with black holes, danced along the edge of space-time, and watched electrons cheat local rules with flashy blue glow. But now, we wade into even stranger waters, the realm of particles that might not just flirt with the speed limit, but absolutely ignore it. The infamous tachyons, the theoretical rebels of physics, the particles that were never invited to the party but somehow keep turning up in the footnotes. Let's not sugarcoat it. Tachyons are weird. According to their definition, they don't just go faster than light. They always go faster than light. They can't slow down. They can't ever move at or below your perfect speed, photon. They live permanently on the other side of the limit, in a zone where all known math begins to whisper ominously, and the concept of cause and effect starts cracking under the pressure. Tachyons have imaginary mass. No, not made up as in fictional, though that's fair too, but imaginary in the mathematical sense, as in the square root of a negative number. If you plug a tachyon into the equations of relativity, its velocity isn't just fast, it becomes untouchable. The faster it moves, the less energy it requires. And as it loses energy, it speeds up. It's like the universe pays it to misbehave. Imagine throwing a ball that gains speed as it cools down. That's a tachyon. And the closer you try to make it behave like a normal particle, bringing it down toward light speed, the more energy it would need. Infinite energy, in fact, to hit the boundary. So just as nothing with mass can reach your velocity from below, nothing tachyonic can descend to it from above. You're separated by a wall neither can touch. Opposite sides of reality's fence, glaring across the speed limit like rival neighbors. Now here's where things go off the rails. If tachyons existed, they could theoretically transmit information backward in time. Not just really fast, but retrocausal. Send a signal to the past. Drop a text to Tuesday from Friday. Rewrite decisions, dodge consequences. You could tell your past self to avoid that gas station sushi. Or worse, send a message that prevents itself from ever being written in the first place. Hello, causality crisis. This is why physicists get itchy around tachyons. It's not that the math strictly prohibits them, it's that if they exist, they break the rules that keep the universe logical. The consequences ripple outward. Cause and effect unravel. History stops being a sequence and becomes a feedback loop. A cosmic game of did I just unhappen? Historians still debate how seriously early theoretical physicists considered tachyons. The term itself was coined by Gerald Feinberg in the 1960s, who explored how these faster-than-light particles might fit into the framework of relativity. At first, they were a curiosity, a playful extension of math beyond its comfort zone. But as more consequences were uncovered, enthusiasm gave way to unease. The cost of welcoming tachyons was too high. You had to mortgage causality to afford them. And yet, the universe hasn't strictly ruled them out. We've never detected a tachyon. No experiment has revealed anything traveling faster than light in vacuum. Not one particle, not one burst, not even a polite RSVP. But some fringe theories still keep the door open, just a crack. String theory, for instance, briefly featured tachyonic modes in certain unstable scenarios, like warning lights telling you your math was about to collapse. In those cases, tachyons weren't real particles. They were signs that your model needed fixing. Still, their presence in theory books persists, like the phantom limb of physics, unobserved, unconfirmed, but never entirely exorcised. So what would a tachyon feel like? If it had feelings, that's hard to imagine. From its own perspective, if such a thing exists, it would never experience time the way you or I do. It wouldn't be able to stop, rest, or reflect. Every path it takes leads backward into what we consider the past. It's motion without reference. Like a movie on rewind, only the actors are confused because they're improvising as they go. The problem is, allowing tachyons into the story introduces inconsistency, not just in one frame of reference, but in all of them. Different observers could see different orders of events, a cause here, an effect there, and no universal agreement on what happened first. That breaks the very foundation of relativity, the idea that the laws of physics are the same for all non-accelerating observers. You'd suddenly need a special reference frame to correct the order of events. That's not just inelegant, it's fatal to modern physics. And yet, human imagination being what it is, tachyons remain a popular toy in science fiction. They're messengers across time, signals from future selves, warning beacons across the cosmic gulf. Time travel devices often wave a hand at tachyon bursts as their plot-fueling mechanism. It sounds technical, plausible, deliciously dangerous. But you, photon, don't need any of that. You don't flirt with paradoxes. You don't backpedal into causality. You are the one constant in this entire chaotic discussion. You define the barrier, the line no one crosses in either direction. You're what tachyons can never touch, what massive particles can never reach. You are the equilibrium between extremes. So while others dream of time machines and reverse motion messengers, you glide on. The one thing we can count on. No retro travel, no paradoxes, no imaginary mass. Just pure, unwavering movement. You don't skip ahead. You don't rewind, you just go. And perhaps, in a universe where everything else wants to bend, flip, and fracture the rules, that quiet obedience is what makes you extraordinary. You're still gliding forward, photon. Tireless, timeless, untouched by gravity's grip or history's weight. But down in the thick of it, in the labs and chalk-covered classrooms of Earth, human minds are refusing to take no for an answer. Sure, the speed of light is a limit, they say. But what if we don't try to go faster than light? What if instead we cheat, not with speed, but with space itself? And this is where we enter the speculative, spine-tingling realm of warp drives and wormholes. Buckle your non-existent seatbelt. Let's start with warp drives, because what could be more sci-fi than bending spacetime to get somewhere faster than light ever could? The idea comes from Miguel Alcubierre, a physicist who in 1994 proposed a solution to Einstein's field equations that, in theory, allows a spacecraft to ride a bubble of warped spacetime. The craft doesn't move through space faster than light. Instead, space itself contracts in front and expands behind it, like surfing a wave that's rolling the ocean under your board. Sounds fake? It's not. The math checks out. The Alcubierre drive uses general relativity's own rules against themselves. The spacecraft stays inside its cozy bubble, never locally exceeding light speed. Meanwhile, the bubble itself moves, fast, possibly arbitrarily fast. But of course, there's a catch, a huge one, several actually. First, energy. The kind of energy needed to create this warp bubble is negative energy density, a form of exotic matter we haven't confirmed exists in usable amounts. You'd need more negative energy than exists in the known universe just to push a Lego-sized payload a few centimeters. That's not a technical hurdle. That's a try again in several millennia kind of problem. Second, stability. Even if you could build the bubble, we have no idea how to stop it without turning the ship, and possibly the destination, into a high-energy smoothie. There's also the issue of radiation buildup at the bubble's front edge, potentially frying whatever's waiting on the other side. Picture arriving at your dream planet at warp and instantly vaporizing it. Not exactly a soft landing. Still, the warp drive idea persists. Scientists toy with modified versions, looking for clever workarounds that reduce the energy demands or skirt around the destroy your destination problem. So far, nothing practical, but it's still remarkable that the equations even allow it. That Einstein's field equations, when taken seriously, hint at loopholes so big they might swallow galaxies. Then there's the even wilder idea, wormholes. Wormholes aren't about warping space around you. They're about punching a tunnel through it. Imagine folding a piece of paper and poking a hole through both sides. The 2 points are suddenly connected, shortened, cheated. That's a wormhole, a shortcut through spacetime that lets you travel light years without ever exceeding light speed locally. You could, in theory, enter one side, take a stroll, and pop out the other side faster than any photon could make the journey through normal space. Wormholes have been part of physics since the 1930s, when Einstein and Nathan Rosen proposed what they called Einstein-Rosen bridges. Later refinements, especially by Kip Thorne and others, explored the idea that wormholes could be stable and traversable, assuming you had enough exotic matter to keep the tunnel from collapsing like a tired souffle. Yes, exotic matter again, the hypothetical duct tape of impossible ideas. So far, no evidence, no wormholes discovered, no shortcuts mapped, but wormholes remain mathematically valid solutions under general relativity, and that's more than enough to keep them alive in theory and fiction alike. Here, where it gets tricky for you, photon. Wormholes and warp drives don't technically violate the speed limit. They just change the map. The photon still takes the long route, the conventional curve of spacetime, but the ship, or the signal, bends the terrain itself. You're not being outrun, you're being outnavigated. It's like racing a friend through the mountains. You take the road, all curves and switchbacks. They drill a tunnel straight through the rock. They don't go faster than you. They just cheat the geography. Still, wormholes bring their own bag of snakes. Time travel, for instance. If one end of a wormhole is accelerated and brought back to the original location, time dilation could cause a discrepancy between the two mouths. You now have a time machine. Go in one side in 2073, pop out the other in 2025. Send a message back. Meet your past self. Prevent your own journey. You see where this is going, back to the dark playground of causality violations. Historians still argue whether Einstein believed in the physical reality of wormholes. He was notoriously cautious about speculative extrapolations from his math, but modern physicists have been braver, or at least bolder. Kip Thorne famously helped Carl Sagan design a scientifically plausible wormhole for the novel Contact. And though the film version turned it into a psychedelic roller coaster, the original math remains among the most realistic treatments of faster-than-light concepts in fiction. Now here's a fringe tidbit that actually has some experimental legs: quantum teleportation. It doesn't send matter faster than light, but it does transfer information, specifically quantum states, between entangled particles. This has been demonstrated in labs across distances of many kilometers, but even here the speed of light is preserved. The teleportation can't complete without classical communication, which is still limited by so again, no violations. Just very clever dance, steps around the edge of possibility. So what does all this mean for you, photon? It means that even in a universe brimming with imagination, where minds dream of bending space and carving tunnels through time, your place remains firm. You are still the standard, the baseline, the thing we are all trying to beat without breaking the rules. And despite every theoretical detour, you're still unbeaten. Warp drives may shift the terrain, wormholes may stitch shortcuts through spacetime, but they don't dethrone you. They just acknowledge how powerful your role is, because light speed isn't something we surpass. It's the thing we work around with desperate creativity and borrowed equations. You don't cheat, you don't skip ahead, you simply go. And the rest of us, we keep trying to fold the universe around you. You glide on, photon, clean, massless, and endlessly consistent, while deep in the minds of physicists, a different kind of light flickers, one filled with riddles, hypothetical creatures, and stubborn little rules. We're stepping away from the grand cosmic highways of warp drives and wormholes to shrink things down, way down, into a strange little thought experiment that has haunted thermodynamics for over a century. Meet Maxwell's demon, a tiny, imaginary imp with big implications. Picture this, it's the 1860s. James Clerk Maxwell, the father of classical electromagnetism, proposes a curious puzzle. Imagine a box divided into two compartments by a wall with a tiny door between them. Inside the box is a gas at uniform temperature, equal parts fast and slow-moving molecules jostling about in random chaos. Now imagine there's a microscopic creature, a demon, stationed at the door. It can see every individual molecule. Every time a fast one comes along from the left, the demon opens the door and lets it through to the right. If a slow one approaches from the right, it lets that one pass to the left. Over time, the right side of the box fills with fast-moving, high-energy particles, and the left side collects the slow, cooler ones. The demon has effectively created a temperature difference, organized energy, without doing any work. That, according to classical thermodynamics, is supposed to be impossible. The second law says entropy must increase or, at best, stay the same in an isolated system. The demon seems to defy that law. It reduces entropy just by watching, just by choosing. But wait, you might say, what does this have to do with light speed? Stay with me. Maxwell's demon poses a fundamental challenge to the link between information and energy, a link that also governs how information travels, and crucially, at what speed. And that brings us back to you, photon. Because information can't move faster than you do. If the demon's trick allowed entropy reduction and somehow encoded information instantly, it would shatter the entire thermodynamic structure of the universe, not to mention the light-speed barrier itself. To really grasp the implications, let's look at what the demon is actually doing. It's not pushing particles. It's just observing and reacting, applying information. And that's the key twist. In the 20th century, scientists like Leo Szilard and later Rolf Landwehr added a crucial insight. Information has thermodynamic cost. That is, just storing, processing, or erasing data has an energy toll. When the demon observes a particle, it must store information. And to keep functioning, it eventually has to erase some of that information, free up memory. And erasing information, according to Landwehr's principle, generates entropy. So in the end, the demon doesn't get to cheat. It just moves the entropy around. And when you account for the energy cost of information handling, the second law still holds. Order may bloom briefly, but disorder wins the long game. But imagine, just for fun, if that weren't the case. Imagine if the demon could process and transmit information with zero cost. Now you've got a system where meaningful information, structure, order, can be communicated faster than the universe normally allows. You've got a way to send a signal without an energy budget, maybe even faster than light. That's where things go sideways. Because the light speed limit doesn't just apply to matter or force, it applies to information. Anything structured, meaningful, or capable of causing an effect is bound by that limit. Let information travel faster than light, and you open the door, yet again, to causal paradoxes, time travel messages, and all the familiar nightmares of retrocausality. Now let's scale it back down to reality. No demon has been found. No entropy-free information process exists. In every known physical system trying to extract or transmit knowledge, whether through heat, photons, or wires, costs energy. And all signals are capped by your speed, dear photon. The message only moves as fast as you can carry it. Still, Maxwell's demon reveals something deep. The universe doesn't just resist motion, it resists cheating. It weaves information and energy into the same tapestry. You can't reorganize one without affecting the other. Every bit of structure you create must be paid for. Every signal you send must obey the laws of causality, thermodynamics, and, yes, light speed. Historians still argue whether Maxwell thought his demon was a serious challenge or just a mental nudge. A playful reminder that physics is as much about what we can't do as what we can. But the legacy stuck. Maxwell's demon became a foundational puzzle in the study of information theory, computational thermodynamics, and the subtle connections between entropy, knowledge, and speed. Here's a fringe tidbit. Some modern interpretations of the demon connect it to quantum measurement. The act of observing a particle, of extracting information, actually alters its state. In this light, the demon isn't just a rule breaker. It's a metaphor for how observation creates reality. It's Schrödinger's cat with a clipboard. And even in this quantum version, the message doesn't travel faster than light. The collapse of the wave function, still not usable for faster-than-light communication. Causality still holds. You still win, photon. So what's the takeaway from this box of gas? This mischievous gremlin, this demon of physics? That light speed isn't just a limit on motion. It's a limit on change, on influence, on how fast one part of the universe can affect another. If Maxwell's demon had worked, if it had truly skirted the second law, it might have pointed to a way to move information instantly, a cosmic loophole. But it didn't, because nature, even in its quirkiest moments, is still deeply consistent. And you, photon, are the enforcer of that consistency. You make sure no message outruns the rules. No cheat code survives the checksum. You are not just a beam of light. You are the speed of communication, the boundary of the knowable, the reason the universe unfolds in an order we can trust. You glide on. No demons chase you. No entropy skips your trail. And the only messages that travel with you are the ones the universe permits. Your flight continues, photon, steady, precise, indifferent to the scale of things. You've flown through vast galaxies and skimmed quantum seas, but now we're pulling you down into a place so tiny, so utterly beyond human scale, that reality itself starts to pixelate. Welcome to the Planck scale, the edge of our understanding, the point at which space and time themselves might just stop being smooth and start being granular. Let's ease in with a number. The Planck length is about 1.616 times 10�3 meters. That's not just small. That's unimaginably, aggressively. Why does this even exist small? It's the scale at which our familiar concepts of geometry, distance, continuity, direction break down. And if you try to go smaller, to probe deeper, the very tools you use to measure start working against you. Now, what does this have to do with you? Well, you're already massless, already timeless, already the universe's designated speed enforcer. But even you don't get a free pass at the Planck scale, because this is where even light might hit its final hard stop. Not speed-wise, you're still moving at sea, of course, but in terms of how finely space itself can be divided. You may not notice it, but the road beneath you may not be smooth. It may be quantized, like a digital image zoomed in so far that you begin to see the pixels. Let's dive deeper. When we look at physics today, we have two beautifully successful theories. General relativity, which describes the large and the heavy, planets, black holes, expanding universes, and quantum mechanics, which handles the small and the weird, atoms, particles, uncertainty. But they don't like each other. Try to combine them and the math breaks. Not like a typo, more like a full-on nervous breakdown. In particular, when you try to model gravity at quantum scales, everything turns infinite. Bad infinite. The Planck scale is where physicists believe the missing theory lives, something that would unify quantum mechanics and gravity. A theory of everything, hiding in this tiny mathematical alleyway. And you, photon, are part of the problem, and maybe the solution. Because even though you're perfectly behaved on every scale we've tested, we've never seen how you perform on the Planck level. It's possible that at that scale, even your journey isn't smooth, that you jitter slightly, or experience spacetime as a kind of granular network rather than a smooth continuum. This leads us to something called loop quantum gravity, a theory suggesting that spacetime is made up of tiny loops, quantized bits of area and volume. In this model, spacetime isn't continuous. It's built from Planck-sized chunks. If true, then motion, even your motion, would be more like hopping from node to node in a vast lattice of geometry than gliding on a smooth surface. And here's the kicker. In a quantized spacetime, the speed of light might still be constant on average, but over very tiny distances, it could vary slightly. That would mean light dispersion in a vacuum, something we've never observed, but that might show up in high-energy photons from distant sources like gamma-ray bursts. If we could detect a delay between high and low-energy photons from the same explosion billions of light-years away, that might be evidence of the underlying grain of spacetime. So far, no confirmed detection, but the hunt continues. Here's a fringe tidbit for your pillow tonight. In some versions of quantum gravity, the very act of trying to measure distances below the Planck length results in the creation of a microscopic black hole. That's right. Probe too deep, push too hard, and spacetime itself curls in on you, sealing off the view. It's like reality protecting its own trade secrets. This concept leads to what some physicists call the Planck wall, the ultimate boundary beyond which measurement, motion, and even definition become meaningless. No signal can resolve anything smaller. No clock can tick faster. No ruler can stretch finer. Not even you, photon, can get around that. You can travel at light speed forever, but you can't make spacetime reveal more detail than it's willing to give. And here, where it gets poetic. The speed of light, your speed, is used to define the Planck scale itself. Planck length, Planck time, Planck energy, they're all built using C, along with a few other constants like the gravitational constant g and Planck's constant h stroke. Your role isn't just in motion, you're part of the measuring stick for the deepest structure of the universe. Historians still argue whether Max Planck, the physicist for whom all of this is named, truly understood the implications of the scale he discovered. Some say he saw it as a curiosity, a natural unit system. Others suggest he intuited that it marked a boundary, a place where our current theories would stop working. Whatever the case, that scale has become the holy grail of modern physics. String theory, another candidate for quantum gravity, agrees that the Planck length is where the action is. But instead of loops, it suggests that fundamental particles, including you in your wave-particle duality, are tiny vibrating strings. And those strings might only vibrate meaningfully when given just enough room, about 1 Planck length in size. Again, a fundamental minimum, a limit, a resolution below which there is no more resolution. It's like saying there are no smaller pixels, stop zooming. So what does this mean for you, photon? That no matter how fast or how far you travel, your journey is painted on a canvas with finite resolution. The lines you trace across the cosmos may look smooth, but they may, in truth, be little quantum hops across a gridded spacetime. You still move at light speed. You still carry energy and information, but your highway might be pixelated, and the speed limit you enforce, it may be built into those pixels, hard-coded at the smallest level of the code base. And we may never know for sure, because we can't observe Planck scale physics directly. Not yet, not with any current technology. It's too small, too subtle, too shielded by the very rules it tries to expose. But in the structure of cosmic microwave background radiation, in the collisions of high-energy particles, in the precise timing of photons from distant stars, you might be leaving clues, little whispers of the granular truth beneath the smooth face of reality. You glide on, photon, unaware of the limits you help define, unfazed by the possibility that the very space you fly through might be built from indivisible dots of geometry. Whether you ride on a smooth rail or hop across quantum tiles, you remain the one constant, fast, flawless, and eternally out front. You're still flying across billions of light years through emptier voids than the human mind can fathom, with no engine, no effort, and no end. You were born in a blaze, perhaps in the heart of a star or the death rattle of some ancient cosmic explosion, and you've never stopped moving. But there's something changing around you. Not in you, of course. You remain perfect, punctual, and unchanged. But the universe itself, the stage you travel across, is beginning to slow, stretch, and cool. You're watching the last act of a very old play, the gradual decline toward heat death. Let's talk about what that means. The heat death of the universe isn't about fire or destruction, it's about stillness. Cold, silent, irreversible stillness. It's what happens when all usable energy is spread out, entropy reaches its maximum, and the cosmos reaches thermodynamic equilibrium. No gradients, no pressure differences, no motion, no work, just a perfectly uniform fog of particles and radiation, quietly existing for no reason at all. Sounds relaxing, right? Well, for you, photon, it's both the end of a journey and the infinite extension of it. You don't slow down, you don't wear out, you're not susceptible to decay. So long as you don't interact with anything, don't get absorbed, scattered, or trapped, you keep going. Forever, but even you will feel the difference. Because as the universe expands, space itself stretches. And with that stretching, your wavelength stretches too. It's not that you're slowing, your speed remains c, but your energy gets diluted. Your once fierce blue blaze becomes redder, then infrared, then radio. Eventually, you become a long, cold whisper, cosmic background noise in a universe too tired to listen. This phenomenon is called cosmological redshift, and it's happening to you right now. As space expands, it drags your wavelength along with it. If you were born as a high-energy gamma ray shortly after the Big Bang, You may now be a microwave photon, one of the billions that form the cosmic microwave background, CMB, the afterglow of creation, stretched thin across the ever-expanding cosmos. And the expansion isn't slowing down, it's speeding up. Thanks to something we still don't fully understand, dark energy, space itself is accelerating outward. Galaxies are receding faster and faster, and as they pull away, more and more of the universe slips beyond our cosmic event horizon, a boundary beyond which even you, photon, can't return. Not because you've gotten slower, but because the space between you and the observer is expanding faster than you can close the gap. It's a cruel trick. You're still sprinting at top speed, but the finish line is retreating faster than you can run. Light emitted from galaxies beyond this horizon will never reach us, no matter how long we wait. And in a few trillion years, nearly every galaxy not gravitationally bound to ours will disappear from view, fading not because they've stopped shining, but because the universe has outpaced you. Historians still argue about how to interpret this final fate. Some cling to the idea of a big crunch, where the universe's expansion reverses and everything collapses back into a hot, dense state. But most evidence points the other way. Endless expansion, a slow fading into a cold, flat abyss. The heat-death scenario, first sketched out in the 19th century by Lord Kelvin and others, now looks like the frontrunner. So what becomes of you in that distant, darkened future? Assuming you're still unabsorbed and still in flight, you'll be almost unrecognizably cold. Your energy, smeared across longer and longer wavelengths, will eventually approach zero. You'll still be moving at sea, but effectively you'll be meaningless, a ripple in the deepest quiet. You'll have no more galaxies to reach, no more atoms to strike, no observers left to perceive your existence. And yet you'll still be there, a relic of a younger, livelier universe. Here's a fun, if slightly haunting, fringe concept. In the far future, when black holes begin to evaporate through Hawking radiation, they will release their own photons, the final sparks of complexity in a cosmos otherwise gone to sleep. These photons will be among the last forms of structured energy to exist, and even then they'll redshift, drift, vanish into meaninglessness. By that point, you may have been traveling for trillions upon trillions of years, your original message, if you had one, long faded into static. You'll have watched stars fade, galaxies disperse, structures collapse. You'll have traced the cooling of everything, and yet you'll remain untouched. You'll still be you. But what does you mean in a universe with nothing left to measure you against? The strange truth is, even photons like you aren't exempt from irrelevance. Not decay, again, you don't decay, but cosmic context. In the heat death, everything spreads out so far, becomes so energetically flat that even the idea of movement stops making sense. There are no observers left to see you fly, no clocks to mark your passage, no atoms to interact with. In a thermodynamically dead universe, you are motion without meaning, flight without arrival. Here's a deeply strange but beautiful way to think of it. Right now, you carry time. By moving at light speed, you define what's possible in terms of signaling, causality, and sequence. But in the far future, even that role fades. If entropy is maxed out and nothing is changing, then the universe no longer needs time in the traditional sense. No clocks tick, no comparisons exist. The stage remains, but the play is over. And yet the laws never changed. The speed of light, your speed, remained the limit. Even as galaxies vanished, stars dimmed, and particles faded into background noise, you kept obeying the one rule that held it all together. Not because you chose to, not because you believed in it, but because that's what you are. You're the reminder that even as things fall apart, they do so with precision, with rhythm, with rules. So you glide onward through colder and quieter expanses. No applause, no finish line, just the long, slow fade into the final curtain of the cosmos. Not broken, not beaten, just stretched into silence. Still you travel, still you shine, however faintly, across a cosmos grown old and dim. No stars call to you anymore. No planets rotate in hope of morning. You photon are among the last moving things in a universe that has nearly forgotten how to move. And yet you keep going. You always have, you always will. Because at the end of it all, past the chaos, past the heat, past even the silence, there's still the rule you carry within you. The one that says, quite simply, this far and no farther. Light speed isn't just a boundary, it's the framework. The invisible line that keeps everything honest. That holds time to its direction and space to its shape. That binds mass and energy in an unbreakable handshake. We've talked through every challenge to it. Twin paradoxes, wormholes, warp bubbles, whispering quantum foam. And every time light speed holds. Not because it resists, but because it defines. It's easy to envy you. You never age. You don't carry mass or memory. You don't stumble or hesitate or feel regret. You were born flying and you never stopped. You move in a straight line through a curved universe. Unswerving, unblinking. You are motion itself, wrapped in a neat little packet of electromagnetic perfection. And yet the price for your perfection is steep. You don't experience time. You don't see what you pass. You don't know where you are. From your perspective, every journey is instantaneous. Every distance is zero. No beginning, no end, just a blur of origin and destination collapsed into one meaningless flash. You are fast, yes, but you're also isolated, not by space, by causality. You are not lonely because you do not feel. But if you could, perhaps you'd envy the particles who move more slowly, those saddled with mass, age, decay, because they get to exist in time. To observe, to change, to experience before and after. They can accelerate, pause, turn around. You never can. You are pure inevitability. That, paradoxically, is why the universe needs you. You keep everything consistent. Without you, there's no fixed speed for information, no defined edge to a light cone, no structure to time. You give the universe its coherence. The cosmic speed limit isn't there to trap us. It's there to protect us from paradox, from contradiction, from chaos. Even mass owes its meaning to you. Without the constant c, Einstein's equation E equals mc2 E equals mc2 collapses. Energy and mass no longer equate. The fundamental connection between matter and motion falls apart. The universe's bookkeeping breaks down. And while you've been many things, sunlight, radio signal, X-ray, gamma burst, you've never wavered in this role. You are the fastest that can ever be, and in that speed lies clarity. Speed not as rebellion, but as a kind of surrender. You are the one thing that cannot choose to be otherwise. Historians and physicists still argue over whether this limit, this speed, is an artifact of how spacetime is built or a deeper, emergent feature of a quantum gravity theory we haven't fully seen yet. Is light speed a universal law or just the sharp edge of a deeper equation? Does it emerge from symmetries, or does it define them? There are hints, so many hints, that it goes deeper. That light speed is not just a velocity but a conversion factor. It links units of space and time, energy and momentum, mass and frequency. In natural units where c equals 1, c equals 1, everything simplifies. It's not just a limit anymore, it's a bridge. The translator between the dimensions of existence. And maybe that's what you are, photon. Not just fast, not just pure, but a translator. You carry energy from one place to another, information from then to now. You cross the gaps so nothing else has to. And though your journey is featureless, silent, empty, you make connection possible. You've witnessed everything without ever really observing it. You've carried the light from the first stars to the eyes of future beings. You've illuminated surfaces, carried signals, sparked seeds of life, and painted shadows that made minds wonder. And what have we done in return? We've tried to chase you, understand you, cheat you, measure you down to the last decimal. We've built machines to catch you, slowed you in exotic materials, bent you with lenses and fields. We've used your limits to define everything from space travel to quantum entanglement. We've trusted that your speed would never change because everything else depends on it. And you never did. Even as the universe grows dark and slow, your presence will remain in the background radiation, in the last Hawking photons evaporating from ancient black holes, in the infinite redshift echo of stars long gone. You'll be there, not as witness, but as remainder. So maybe it's beautiful that nothing with mass can reach your speed. Maybe it's right, because chasing light is chasing perfection, and perfection, by definition, is unreachable. That's what gives the universe its shape. That's what makes time tick in one direction. That's what makes stories have beginnings and endings. And you are the line that cannot be crossed, the thread that stitches every page together. You are the speed of light, and that is enough.